Good evening. We're going to be doing 11.2 notes here as soon as I set this up. All right, so that's what you have right there in front of you, notes 11.2. And so let's take a look. So this is about arcs and their measures, so the arcs of a circle. The central angle, a little definition here, the central angle is an angle whose vertex is at the center of the circle. So angle ABC would be a central angle because the vertex B is the center of the circle. And an arc is an unbroken part of a circle consisting of 2 points on the circle and all the points on the circle in between. And so an arc would be, an example of an arc would be arc AD. The 2 points A and D and all the points in between that I've covered here in red. A minor arc is an arc that's less than 180. And those will usually be denoted by 2 letters. So like we have here, if I can erase these, that arc AC. The measure of arc AC, the measure of an arc is equal to its central angle. So the measure of arc AC is equal to the measure of arc ABC, which is 93 degrees. A major arc is an arc that's 180 or more, and so that would be like arc ADC. I have to use 3 letters to talk about a major arc because otherwise they won't know to go in that direction. So if I just said arc AC, you wouldn't know if I meant arc AC, this green one, or arc ADC, the red one. So we have to use 3 letters so everybody knows. And since the full circle is 360 degrees, the measure of that arc ADC is equal to 360 minus this central angle here, which is essentially this angle, the rest of that angle inside. So 360 minus 93 would be 267 degrees. If the endpoints, I'm looking down here, if the endpoints of an arc lie on a diameter, the arc is a semicircle, which is half the circle, and its measure is 180 degrees. And so let's look at our arc addition postulate. The arc addition postulate basically just says the measure of arc ABC, this arc here, from A through B to C, starting from A through B to C, is equal to the sum of the 2 arcs that make that full major arc up. So that would be measure of arc AB, measure of arc AB, plus the measure of arc BC. So plus the measure of arc BC. So it's pretty much like the angle addition postulate and the segment addition postulate. And let me move this up a little bit here. So let's look at our example 1, find the measure of each arc. I want to find the measure of arc CD. The arc CD is equal to its central angle, which is 148 degrees. Its central angle is the angle here that intercepts the arc. So CD is equal to 148 degrees. The measure of arc CDB, starting from C, going through D, all the way to B, is equal to this 148 here, plus the whole other half of the circle. What's a half of a circle? 180 degrees. So that's going to be equal to 180 plus 148, which is 328 degrees. Let's look at the measure of arc BCD. So BCD, this is going this way, starting from B through C all the way to D. That's half the circle. That arc's endpoints are on the diameter, or the endpoints of the diameter. So that is half a circle, which is 180 degrees, half a circle. And now let's look at BC. So let's see, BC, just this right here, this little minor arc right here, BC. Now we said that BCD is 180 degrees, that's half the circle. So BC must be 180 degrees, that whole half minus the 148 degrees. And so arc BC must be equal to 32 degrees. Let's move on to our next example here, our next theorem. Our theorem says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So this is basically saying that if two chords are congruent, like, wait for it, like AB and BC, those two chords are congruent, therefore their arcs are congruent. So AB, this arc here, AB, is congruent to this arc here, BC. So, and it's if and only if, so it goes the other way too. If arc AB is congruent to arc BC, then segment AB is congruent to segment BC. So segment AB is congruent to segment BC. So it works both ways. If the chords are congruent, then the arcs are congruent. If the arcs are congruent, then the chords are congruent. So let's look at example 2. It says RS is congruent to segment TU. If those two chords are congruent, then their corresponding arcs are also congruent. So arc RS is congruent to arc TU, and therefore their measures are equal. So we have 3x equals 2x plus 27. And if I subtract 2x from both sides, then x equals 27. Now they want the measure of arc RS, the measure of arc RS, and that should be equal to 3x, so 3 times the value of x, which we found out was 27. And so 3 times 27 is 81 degrees. So the measure of arc RS is 81 degrees. Let's look at our next example. This is using the same theorem here. It says that this ray PT here bisects angle PRS. So that means this ray bisects this angle, and therefore, if it bisects the angle, it breaks it up into two congruent angles. So these two central angles here are congruent, therefore their arcs are congruent. Therefore, arc RT is congruent to arc ST. And if the arcs are congruent, the chords are congruent. So the chord ST is congruent to the chord RT. Congruent. And therefore their measures must be equal. So 6x must be equal to 20 minus 4x. If I add this 4x to both sides, then 10x equals 20. And if I divide both sides by 10, x equals 2. They want RT, so let's find RT. It says RT is 6x, so RT equals 6 times whatever x is. We found out x is 2, so RT equals 12. All right, let's move on to our next two theorems. These are very interesting theorems. If a diameter of a circle is perpendicular, if a diameter of a circle is perpendicular to a chord, this chord right here, then it bisects the chord and its arc. So in this example, that diameter bisects the chord and it bisects the arc. Bisects the chord and bisects the arc. In other words, cuts the chord and the arc in half. So if DE, if segment DE is congruent to segment EF, then arc DG is congruent to arc GF. And this is basically, the next one is basically the converse of that. If one chord is perpendicular bisector of another chord, then the first chord must be the diameter. So this chord here, JK, is perpendicular to and bisects ML, therefore JK. Segment JK must be the diameter of the circle. So let's look at an example that uses this. Example 4. Example 4 says find BD, and so I have a a radius, which, oh, excuse me, I have a radius. Well, what happened? I have a radius that is perpendicular to a chord, therefore it bisects the chord, and it also bisects the arc. We're not going to use that right now, but it does bisect that arc too. So if it bisects the chord, let's see, how's that going to help me? I know this CD is congruent to CB. I also know the radius of this circle, don't I? What's the radius of this circle from A to E? It's 3 plus 2, so that's 5. How does that help me? Maybe I'll draw, anywhere I draw the radius, it should be 5, right? So maybe I should draw a radius to D. And I know that that is 5 because all the radiuses are 5. And so I have a right triangle here with a leg of 3 and a hypotenuse of 5. And so I can find what CD is by using the Pythagorean theorem. So I have 3 squared plus CD squared equals 5 squared. 3 squared is 9. 5 squared is 25. And if I subtract 9 from both sides, CD squared is 16. And CD equals 4. If I take the square root of both sides, CD is 4. If CD is 4, then BC is 4 because that radius bisects that chord. And so BD is 4 plus 4, or 8. Now we have one more theorem here. This theorem does not appear in your book, but it could come up on one of your exams. So I wanted to make sure that we saw it. So let's look at this. It says theorem 11 point asterisk. If in the same circle or in congruent circles, two chords are congruent, so chord AB, give me a second here, chord AB is congruent to chord CD, two chords are congruent, if and only if they are equidistant from the center. So EG and EF represent the distance, and so if these two distances are equal, then the two chords are congruent. So chords have to be equidistant from the center in order to be congruent. So AB is congruent to CD if and only if EG, that distance, is congruent to EF, that distance, the distance from the center to the two chords. And so if I apply that here, it says AB is 12, so I know that AB is 12, and it says DE is 12, so I know I have two congruent chords. That means they should be equidistant from the center. That means this length here should be equal to this length here. They should be equidistant from the center C. It says CE is 7. Find CG. To find CG, I could also find CF because they're the same length. So let's find CF. Why should I find CF? Because for one thing, I have CE. That might help me. And for another thing, I also have FE, if you caught it. It says that DE is 12, and I see that this FC is a radius, right? It will be a radius if I extend it. And it is perpendicular to DE. And if a radius is perpendicular to a chord, then it bisects that chord. And therefore, this length is half of 12, or 6. And so I have a right triangle here with a leg of 6, an unknown leg, and a hypotenuse of 7. So I should say 6 squared plus CF squared equals 7 squared. You might not be able to see that CF because I wrote all over it, but there's that F. So now we have 36, 6 squared is 36, plus CF squared equals 49. And if I subtract 36 from both sides, then CF squared equals 13. And if I take the square root of both sides, then CF equals the square root of 13. And CF, and we said that CF is congruent to GC because chord AB is congruent to chord DE. If two chords are congruent, they have to be equidistant, the same distance from the center. And so these two segments here represent the distance to the center. And so GC must be the same as CF. So it must be equal to the square root of 13. And that's it.